Hi, I'm Changyuan Lin, a master's student from the University of Alberta. I'm going to present our paper, A Large-Scale Dataset and Empirical Study of Docker Images hosted on Docker Hub. This work is in collaboration with Professor Sarnadi from the University of Alberta and Professor Hamza Kazai from the York University, Canada. So what is Docker? Docker is a popular containerization solution providing lightweight virtualization. That's for sure. Docker can package an application into an easy-to-deploy image. The Docker image is defined by Dockerfile, which is basically a sequence of commands that specify how to build a Docker image. Docker provides version development through tagging. Similar to GitHub, we also have Docker Hub, which is a Docker image registry, and there are millions of images hosted on it. So we already have few relevant papers. Why do we need a new dataset and another study? While most of the Docker datasets were collected like 3 years ago, and they did not study evolution trends, and they collect the data solely from GitHub and focused on Dockerfiles only. So those Dockerfiles may not come from real-world Docker images, and they lacked information about the Docker images and thus had limited research questions. So how to gather information about Docker images? Of course, from Docker Hub, where images are hosted, but how to pinpoint the corresponding source repository of Docker images? The answer is still from Docker Hub. Docker Hub provides a continuous integration service that can link your image with a GitHub or Bitbucket repo. So you can use this CI service to set up the automated build. When there is a new commit in the repo, an image build is triggered automatically. And Docker images using this CI service will have a link to their source repo in their description page. Okay, now let's talk about the methodology of dataset curation. First, we developed the Docker image miner, which can gather image info through Docker Hub API. We also developed the source repo miner. For a given GitHub or Bitbucket repo, it can collect the repo info, commit history, etc. Through the CI link collected by Docker image miners, source repo miners can collect the corresponding repository information. We also match some repositories by the image name. Then we persist the collected data in a PostgreSQL database, and our empirical study is based on this newly collected dataset. Here's the schema of our dataset. It has 10 tables collected from 3 sources, contained over 3 million Docker images and over 300,000 source repositories. Our dataset covers over 98% of public images hosted on Docker Hub as of May 2020. The dataset is publicly available at Zenodo. So based on this newly collected dataset, we conducted 4 research questions, including the characterization of the Docker ecosystem, tagging practices, coevolution behaviors, and smells in Dockerfiles. Okay, the first research question. What is the current state of Docker image development and how did it evolve over time? We investigated 5 aspects. First, programming languages of the containerized applications. We can see Shell is declining, while Python, Go, and JavaScript are increasing in popularity. Regarding the base image, we can see the clear decreasing trend for Ubuntu and an increasing trend for Alpine, Node, Python, and Go. Interestingly, the OS-based images are decreasing in popularity while the programming language and application images are increasing in usage. We studied the evolution trend of the Ubuntu-based image version. We can see around 2019, there is a surge in the usage of obsolete Ubuntu versions, so developers should be aware of such a problem, as obsolete operating system-based images may pose serious security risks. Regarding image architectures, not surprisingly, x86 is a predominant architecture, but we can say ARM-based images are growing really fast. The Docker image size seems to decrease over time as the median drops from around 190 megabytes to around 120 megabytes. This is good news because keeping the image small is one of the official best practices of developing Docker images, and it is followed by more developers. Okay, next research question. What are the current image tagging practices? Docker provides version development through tagging. An image may have many versions with different tags. Release tagging and SH panning are 2 popular tagging practices. Release tagging basically means making the tag point to a stable release version and using the release name as the tag name. SH panning means using commit hash as the tag name. We find that release tagging is favored by more developers. Then we studied the problematic latest tag. So why problematic? For example, the image may only have one default latest tag. In this case, there is no version control at all, which is not recommended. Sometimes the default latest tag may not exist. In this case, the Docker engine can't find the image if developers do not explicitly specify the tag. Sometimes the latest tag may not literally mean the latest version. For example, in this Docker image, the latest tag points to a version that is lagged by 4 versions and 5 months in update time compared to the real latest release version. We refer to this as the version or time lag problem. So we studied how serious these problems are in practice. We found that 1.5 million images only have the latest tag. About 1 million images do not have the latest tag. Around 11% of images have a latest tag, but the latest tag does not point to the latest version. And we also observed some large version or time lag problems. Okay, RQ3, how do Dockerfiles co-evolve with source code? In a Docker image source repository, there should be a Dockerfile for building the image and application source files to achieve functionalities. Because Dockerfiles and source files are different in nature, we studied their co-evolution behaviors regarding the scale and the rate of changes. We basically compare the number of changed lines and the ratio between the source repo commit count and the Dockerfile commit count. We found that Dockerfiles evolve at a smaller scale than source files in terms of the change line count. Dockerfiles also evolve at a slower rate than source files, and this rate continues to slow down. RQ4, how prevalent are code smells in Dockerfiles? While Docker has some official best practices of writing high-quality Dockerfiles, we use Headlink to check if there are smells in Dockerfiles violating those best practices. We found a downward trend in the smell count. This is good news as it suggests small developers could write high-quality Dockerfiles. We also studied the evolution of prevalent Dockerfile smells. Smells causing larger image sizes are declining over time, but smells like not catching the pub error and incorrect command usage become much more prevalent. Okay, so what implications do I bring to the Docker community? First, for Docker image developers and technology providers, they need to avoid using obsolete-based images, and always check the error-prone latest tag. Continue to follow the best practices of keeping images small. Of course, avoid some prevalent code smells. For technology providers who want to promote their products, creating a ready-to-use base image is a very good choice. For Docker and infrastructure providers, first they should consider adding support for fast-growing ARM architectures, providing a tool to check the latest tag, and integrate the obsolete base image checker into their existing CI service and catch some layers of popular base images. The dataset is at Zenodo, and artifacts are available on GitHub. Please definitely check out. That's pretty much it. Thank you for listening.